We're in Algebra II, 9.1d, and we're going to determine even or odd functions. If you haven't seen the 3 previous videos for Chapter 9 that we've done so far and you get lost or confused, go into this description and click on the links and figure out where you got lost, okay? And then come back to this one. So in 9.1b and 9.1c, we talked about these 2 theorems, okay? So in 9.1b, we talked about 2 points are symmetric with respect to the x-axis if and only if their y-coordinates are additive inverses and they have the same x-coordinate. So we would have the same x-coordinates, 3 and 3, see that? But the y-coordinates are additive inverses. We have a 2 and a negative 2. And 2 points are symmetric with respect to the y-axis if and only if their x-coordinates are additive inverses and they have the same y-coordinate. So now we've got additive inverses for the x, the 3 and the negative 3, and that y-coordinate's the same. They're both 2. So the 2 points would be symmetric with respect to the y-axis. See that? And the other theorem we talked about in 9.1c, a graph of a relation defined by an equation is symmetric with respect to the origin if and only if replacing x with the inverse of x and replacing y with the inverse of y produces an equivalent equation. So it would be like these two. X squared equals y squared plus 2, and the inverse of x squared equals the inverse of y squared plus 2. See? And they're equivalent. So I want you to remember that we've talked about this before for x and y. They have a lot of different names. Y can also be the function of x, okay? So they have a lot of different names that we call them. The functions whose graphs are symmetric with respect to the y-axis are called even functions. So take a look at these 2 graphs. Are they symmetric with respect to the y-axis? Yeah, they are. See, we have our y-axis here, and these are symmetric to the y-axis, aren't they? So we know these are even functions, okay? Let me remove these so we can continue. So if y equals the function of x defines an even function by that first theorem, then y equals the function of the inverse of x will define the same function. Here's a definition. A function is an even function when the function of the inverse of x equals the function of x. So it's like saying when a negative y equals the y, okay? So like squared, because we know that function of x can be a y, can't it? And this would be for all x in the domain of f, okay? So it's going to make more sense as we move forward. Functions whose graphs are symmetric with respect to the origin are called odd functions. So take a look at this graph. This is symmetric to the origin, isn't it? It's not symmetric to the y, so it's not an even. We don't have an exact reflection on this side of the y-axis, do we? It's reflecting across the origin, so now that's an odd function. So if y equals the function of x defines an odd function, then, by that second theorem, the inverse of y is going to equal the function of the inverse of x. We have another definition. The function is an odd function when the function of the inverse of x equals the inverse of the function of x for all x in the domain of f. You're probably tired of hearing the word function by now, aren't you? Okay, so let's continue on. So remember, we can say the function of x for y. Okay, so that'll help with some of the confusion. We can determine, I'm missing an e here, aren't I? We can determine whether the function of x equals x squared plus 1, if it's even, odd, or neither. So here we have the function of x, and here we have the function of the inverse of x, okay? And it says it equals x squared plus 1. So that means we would have the inverse of x squared plus 1. So we compare these two, and they are the same for all x in the domain, so the function is an even function. Because we ask ourselves, does y equal the function of x define y equal the function of the inverse of x? Yeah, because when we simplify this, we get x squared plus 1. See? The same thing. So we know it's an even function. So now let's compare this one and this one, okay? We're going to compare this f of inverse of x with this one. So we compare them, and they're not the same for all x in the domain. The function is not an odd function. We asked ourselves, does y equal the function of x define the inverse of y equals the function of the inverse of x? And no, see? Because when we distributed this negative, we ended up with a -1 over here. That's not the same, is it? See? We can get examples of even and odd functions from power functions. So the function of x equals x to the nth power, where that n is a little integer. After substituting several values of n, we realize some generalizations. So we've got the function of x equals x to the nth power. Well, it's an even function when that little n is an even number, like a 2 or a 4 or a 6, so on. And it's an odd function when that little n is odd, like a 1, a 3, a 5, 7, 9, etc. Okay? So, since y equals x squared is a function, we can write it as the function of x equals x squared. And the ordered pair for x and y of a function can be written as x and the function of x. Okay? Our next video is 9.2a. We're going to talk about vertical translations, where y equals x squared and y equals x squared plus 1. So we're going to have a figure that's going to translate up 1 unit because of that plus 1. We'll talk about that in the next video. I'll add this video to the Algebra II playlist. I'll have a link to last year's 12.4 video from Algebra I when we talked about quadratic functions. And I'll have a link to the 3 previous videos for this chapter that we've talked about so far. So you can just click on them very quickly and easily. All right? So if you missed me talking about these theorems, go back into the description and watch those 2 videos, or all 3 if you can, all right, so that you don't miss any steps. And I hope you're having a great day. I'm really proud of you for watching math videos, and I'll see you next video. Bye.